It's algebra.
I didn't submit, so.
Yeah, I know you didn't.
So maybe we can begin. Let me just emphasize in the notes. I made two references. Well, I don't know if you read the notes, maybe you don't read the notes. The literature. That I strongly recommend. One is the book of Arnaud. This is the standard textbook in ordinary differential equations. It's one of the finest books I know on any subject. And this is a textbook for his basic course in Moscow. And Palais is a Russian, this is an American. A basic research monograph on a basic research monograph. If you are interested in it and you can't find it, I will find it for you. I gave the exact reference in the notes. Let me just say what this is about. So it's on globalization of local actions. Let me remind you what the fundamental theorem says. I will draw a picture of it. Here is the manifold M, and X is a given vector field. We talked about this, but perhaps not in enough detail, and I talked in great detail, more detail in the notes. Then there's some region about M, about in M cross R. Maybe I should color it in. So this is a nice region, this is an open region. And maybe I'll call it D. This is the domain of definition. Of the local one-parameter group action. And what this means is, if you take an initial value here, x, it means that you can integrate the field for this much time. We've seen that you can't integrate globally necessarily. We had examples where you reach a blow-up. Remember this field here was, even in one dimensions, was a case where you cannot integrate globally. Globally would need for every time. So here is a point, here, time, and x. Yeah, so for time and the time axis, and x and m. And the domain of definition is where the action is defined. So this a point tx goes to the local action gt of x. So this is a smooth map in this product region, which is very mysterious in some sense. There's a smooth map, and we know that the vector field is then given by, well, let's say x, and x is given by differentiating a function along this flow. Now, to be precise, I should say here what I've done. I've differentiated a function at f. Let me repeat. There is a region about M here, which is open, and if you take any segment, any copy of the real line here, that's how far you can integrate in the time axis. This is an interval of integration. That means you can integrate this field to get these local diffeomorphisms so that the field is given by this action. Okay. This is a one-parameter group where it is defined. So G of T composed with G of S is equal to G of T plus S wherever defined. So you integrate here and you come to some new point in the manifold, maybe here, and well, it's just all three things have to be defined for it to make sense. Okay, this is called the domain of definition of the local one-parameter group. Okay. Yeah. This is the fundamental theorem of all ordinary differential equations. Okay. Every ordinary differential equation can be integrated in this sense. There's a region here which is open, and I've told you all about it. So that defined on this region, you have this local one-parameter group. It's local because it is not defined for the whole region R. Okay? So you know for linear fields and many fields you have global one-parameter groups. Right? Here you have only local one-parameter groups. Okay? This is the fundamental theorem of ordinary differential equations. I did not prove it. I will not prove it because it takes some time. The difficulty is not so much the existence of an integral curve. You see what we're doing here, we're integrating a field, and we have a base point x, and we have gt of x flowing around this field, flowing along here, and you've integrated the field along this curve. This is not so difficult to prove. What is more difficult to prove is what people call the smoothness of the dependency on the initial condition. The smoothness of the you move this initial condition and you have a new integral curve, right? You have a new solution, and you see this function here as a function of two variables is smooth. That means that the integral curve, if you move it, depending on, you go to a nearby condition y, here's gt of y, along here you've integrated, that it depends smoothly on the initial condition. It's as smooth as a function of two variables, as a function of time and of the point, the initial point. This is slightly non-trivial theorem and takes some time. You will find it in Arnold's book, but in an appendix, so that proves that even Arnold, who was a great teacher, I think, decided maybe not always to prove this theorem because it just does not reflect too much about the subject. But the theorem is a wonderful theorem, the fundamental theorem of ODE, ordinary differential equation.
Professor, I have a question.
Yeah.
This Saturday we were discussing a related problem. So if our vector field has a compact support, then we can have a global solution.
That's right.
Is that true or no?
What?
I want your remarks.
Say it again.
I want your remarks about it.
Yes. So I commented on that in the notes, and I wasn't going to comment about it, but I will comment on it now thanks to his question. So there's a word in mathematics called compact support. Okay? I think I should comment on what that word means, so everybody's on the same page, and also the statement that you just made. So the first thing is, what is the support of a vector field? You should think the support of anything is where it's not zero. okay? But the best way to define it is the complement of the set of points where it is locally identically zero. Something is locally identically zero means it's identically zero in a neighborhood. Okay? So you see, you're differentiating. You're differentiating this field with this field. The field could be zero at this point, but I mean, when you start moving, it goes away. I mean, that would be something interesting. So you're interested where it's really locally identically zero. Nothing happens. Okay? So the support is the complement of the set where it's locally identically zero. Okay? Or the closure of the set where it's not zero. So on the boundary you have something. That's the support of the field. Okay, that's the first thing. The second word here is the word compact. Now, you should think, so mathematicians who have experience with this is a very fundamental concept in mathematics. I think it's one of the most fundamental concepts in all of mathematics. So the first word, when you hear the word compact in mathematics, you should think small. You should think bounded. Okay? So, if you have an abstract manifold, it's very hard to say what does it mean bounded. Right? It's just some abstract thing. What does it mean bounded on it? Okay? Well, I propose the following thing. You can't go to infinity in this set. So, I would like to say, here's a manifold, and in German the letter, not the word compact starts with K, so these compact sets are quite often called K. When you see the letter K, it always means compact. You should think it's some bounded set like that, okay? That's already good enough if you think like that. It's bounded and it's closed. So that's not really, the key issue here is bounded. Okay? And the word bounded means you can't take off to infinity while staying in this set. You see, infinity is outside of here. Here's the way you go to infinity. So if you take some sequence in here, there's just no way to go to infinity. How do you define infinity? Okay? It's everything out there. Okay? One definition of not being able to go to infinity is that no continuous function on the manifold blows up along a sequence. You see, if you have a continuous function on a manifold, and this, think of it intuitively, if you have a bounded set, whatever the hell that means, you have a bounded set in this thing, you have a continuous function way out here, and you have a sequence that's staying in this thing, this continuous function is going to take its maximum someplace on this bounded set, right? So there's no way that you can, this continuous function is going to blow up along this sequence. You can't go to infinity means you can't blow up along with a continuous function. That's a correct definition, by the way, yeah?
Is it also an equivalent definition with the finite subcovering of it?
Yes, but you see, that's a mathematical thing. So there are many definitions I can go through now. Okay. Every sequence has a convergent subsequence. Every covering of this set by open sets has finite subcovering. But intuitively, it is much better, and this is not told to you by your beginning teachers. Yeah? If you have a sequence, you can't blow up a continuous function along that sequence. That's really the statement of compactness. Right? Okay? You just have to have a feeling for it. It's bounded somehow. So for example, if the manifold itself is compact like a sphere, then everything is bounded. Right? But if the manifold is Rn, well, you see, bounded means, well, it stays inside of a ball. And if you wish to think of it that way, that's fine with me. Okay? So we have support and compact support. So that's small support. So the theorem is, this is what Latif was saying. So the theorem is, if X has compact support, then every vector field, then X has compact support, then X is globally integral. I.e., there exists a global R action So I'm global, the domain of definition is global. Which integrates this flow field, which means that x of f at x is just given by differentiating along this R action. Okay, this is what you meant, right? Isn't this beautiful? Isn't it really beautiful? These vector fields contain a hidden group somehow. This is a group, a really group, R action. The real numbers are acting as a group of symmetries. It's a fantastic statement. Yeah? And now how to apply this thing? How to use this thing? Well, you give me a vector field. Latif gives me a field and says, look, this field is a catastrophic field. Right? I say, where do you want to understand this field? You know, what do you want to understand about this field? Well, he says to me, I only care about this region here. Okay? I don't care what happens out there, who cares? By the way, physics people always have some region they're interested in and just throw away data outside. So this happens quite often. Right? Latif says that. I said, okay, Latif. So Latif says, only on K, compact, some bounded region is interesting. Well, then I say, I'm very grateful for that because I say here is K, it's bounded, and I say here, I'm going to have a cutoff function which is 1 here, goes down to 0 here, yeah, here's 0, here's 1, this cutoff function I always call chi. The field Latif gave me, I didn't write it, it was called x. I replaced the original field x by chi times x. I cut it, I kill it at infinity. If you're not interested in what's happening way outside, kill it out there with a cutoff function. I'm sorry so violent, I'm not really a violent person. Eliminate the difficulties near infinity. Yes? Okay. But you see what I mean. You cut it off with a cutoff function, and you have a field with compact support. Now it's suddenly globally integrable. Now, of course, I've changed the dynamics terribly near here, on the boundary of here. But inside, I've changed nothing, in some sense, locally. Okay? As soon as you start having flows that would have gone out here like this, they can no longer go out here like this because I've killed off the flow. Right? But still, at least in terms of my local considerations, it's okay. This is a wonderful statement, right? You can kill off the problems if you're only interested in local phenomena. Okay? So every field with compact support is globally integrable by one parameter subgroup. That's something you can say before breakfast in the morning. Okay? Yeah? That's, I think, what you meant. Thank you for the question. Yeah?
How do you define compact in a space of functions?
This is another question. So, Mihai's question is, here I'm not defining compact in a space of functions. I hope I'm not so he asked about function space and compactness in spaces of functions. I'm not sure why you asked in this context. Do you see something here that is bothering you?
So this vector field.
So the set that Latif gave me
Oh, it's
is in the manifold,
Oh, okay. Okay.
because the support set is in the manifold, right? Yeah, but Miha's question is also very good, of course. If we're in some function space, instead of just a finite dimensional manifold, this becomes a totally different problem, right? Compactness is this is all very nice in finite dimensions, this word compactness. But in the physics world, many spaces are infinite dimensional, and compactness becomes a very, very different matter. You look for compactness, you look for compact phenomena. Compactness is bounded somehow. You look for that. We have words like compact operators and various other things. You look for compactness, boundedness. You see, there are spaces in physics called Fock space, where you have really, in quantum mechanics, you have all sorts of operators. And the problem is, it's very difficult to get any kind of compactness going on with these operators. It makes life very, very difficult. Okay. So, that's just a word. Any other comments? That's sort of the end of my remarks about vector fields. So new today, theme for today then, is one form. So for this, I will just say ahead of time, these are dual objects. Two vector fields. And in some sense, it will sound crazy, it's a dual object, but in some sense, you can argue that the dual object is more important than the object. That's a stupid statement, probably. But you can even see this in a vector space. You have a vector space, V, and you go over here to this dual space, and what is this space? This is the space of linear functions on V. And I don't know about you, I understand functions a lot better than I do vectors.
Should be from V to F.
What about you? Thank you very much. So in this case, to the real numbers, or to the complex numbers that they're in. Who made that nice remark? Here, whatever. Oh, here. Yeah, linear functions. And then you take products of linear functions and get polynomials and so on. To me, functions are the things that I deal with. So somehow for me, the dual object is more natural than the object. But that's just maybe a taste. Well, let's take a linear function. And of course, you know what it respects the additive structure of this thing. But the main thing is that if you multiply a vector times a constant, apply the function, that's the same thing as pulling it out in front. Say we're doing over, for example, we're doing over the reals. It respects a scalar multiplication, right? It respects the multiplication by a constant. You dilate the vector by a constant and apply the function. The same thing, apply the function and dilating the vector. That's a heck of a good statement, right? Now, Here we're dealing now with vector fields. Okay. So, what plays the role of the scalars? This thing here, let me just call this as a scalar. This thing you can add two vector fields, right? So that's the additive structure. You can multiply a vector field by number and get a new one. But in physics, this number should be allowed to vary as you move the field, right? You might be in a situation where it's getting stronger and stronger as you approach something, so you can multiply by a function, right? There's no question about it. So if you have a function, then of course you multiply by it and you still get a vector field. Functions play the role of scalars. Let's see, roll. I never know, roll. What do you eat? No, that's American English, I don't know. When you're rolling on the ground. So, I don't know, is that the way you spell roll?
No. Okay.
That was a big E. What did I say, scalars. So linearity means L of fx equals f L of x. Okay? In fancy words, the vector fields are modulo over the C infinity functions, and linearity means with respect to this module structure, which means with respect to multiplication by a function. Okay? So, but it means just that, so let's not be fancy. It just means you can pull out a function in front. Okay. So E1 of M, this notation will become understandable soon. This is space of, this is the dual space, the space of vector fields. And this means duality as a module. So with respect to multiplication by functions. So I again emphasize omega. I will quite often call these things such letters as omega, Greek letters, and f, a function. And now you're going to hate me. Let's start simplifying the notation. Let me call this just E, or E0. So I'm now going to introduce a new notation for the function, just E. Okay, or I could put E0. Functions you should think of the 0 level, and now what I've defined here is the 1 level. Okay, one forms function. So these are the functions. Then f omega of f times this is f omega. Of course, omega of x plus y. The linearity is equal. So the vector space axioms, the usual axioms, except the coefficients of function. So omega here is called a one form on n. And that's the reason for the number 1 up here. It's called a one form. Very soon we will be entering the realm 2 forms, 3 forms, higher order tensors. But so far we do not need anything like that. In physics you will need this all of the time. But this is somehow the first level, the one level. Okay? It's called a one form. Now I'm going to do something exciting. God came to Jacobs University. It's a very dangerous topic. I will not talk about God. So, and decided that there is an operator from functions to one, not only decided, so maybe some of you are Christian, maybe you know this word canonical. Canonical comes from, canonical seems to me to be a Christian word, I think. Canon. I know that from Bach, from music, but it's actually, I think, historically a canon. And said that there's something canonical here. So God came and gave us something canonical and defined a D operator from functions to one forms, which is defined by this. This is another argument for one forms being better than vector fields. There is a canonical mapping called D. I just defined it for you. D of a function applied to a vector field is the vector field applied to the function. I'm sorry, that is really stupid, but it is a fact and very, very fundamental in the subject. Again, is this clear? D of a function is in one form. I have to tell you what it does to a vector field. Well, I apply the vector field to the function. Okay? This is a God-given one form. D of F. Those of you who have done a little bit of mathematics would immediately say, well, what would be the image of this thing? That would be interesting. What forms, you've heard about this in physics, what forms are in the image? Forms in the image are called exact forms. Yeah? You might be curious about what's in the kernel of this mapping, what gets mapped to 0. So interesting questions here that we will discuss, of course, intensely. Interesting question is, what the heck is the image of this thing? And what is the kernel of this thing? The kernel of this thing, I hope you know the notation by now, is the functions which get annihilated completely, which go to the 0 function. Here. We will discuss the kernel today. That's not a serious matter. The image is a serious matter. Okay? Oh, the kernel is also a little bit interesting. Okay. So we have vector fields. The dual objects on vector fields are one forms. That's just the word. Okay. Dual means linearity with respect to function multiplied by functions. And immediately we have a very interesting operator or mapping. I will formulate a lemma which I will suggest that you prove for our homework exercise is if x is identically 0 near a point P and omega is a 1 form on M, then omega x is identically 0 near P. Well, I'll tell you how to prove it. If something's identically 0 near P, see P? Out here is terrible. Okay? Well, then I multiply it by a function, which is a cutoff function, which is 1 near P, and is 0 where this thing's identically 0, and kills it out here. And then I apply omega to chi times the cutoff function times x. Well, cutoff function comes out front. Okay. That proves this lemma. Okay? That's very good. And what this implies is 1 forms are local. This means that you can restrict 1 forms to open sets. How we do this we do this locally with, yeah, but on an open set, it's the whole thing we talked about in the other thing. You have a vector field that's completely insane on the boundary of this open set. You want to define the restriction to this. Well, you cut it off and then show that it doesn't matter how you define it locally, and that's the lemma you need. Okay, so our local, i.e. omega restricted to some open set makes sense. Okay. Now we're really going to have some fun. You're going to learn something today you didn't know. Okay. So for example, let's let u x be a coordinate chart. Okay, that means I can restrict. Okay. Now, the vector fields on a coordinate chart have a frame is a frame. Right? Every vector field is a linear combination of these vector fields, but the coefficients are functions. So a frame in the sense of scalars being functions. Let me just write it here. Every vector field is a linear combination of these things, where these AI are smooth functions. You know that. I've said that 1,000 times. Okay. All right. Well, go back to 8th grade and you say, well, you got a vector space and you have a basis, and well, the professor calls this a frame because it's an ordered basis, and he's thinking of something like this. And then somebody tells you to go to the dual space, and then you say, well, I've got the dual basis. This is dual basis, and of course, that's just the condition that if you apply the function to the basis, you get either 1 or 0, right? That's the dual basis. Right? We learned this. This is the good basis. Once you have a basis in the vector space, then you have a dual basis. Once you have a frame in a module of this type, we go to the dual frame. It's the same thing. Precisely the same thing. Now you're going to be incredibly happy because you're going to learn something you've seen all your life, you're going to learn what it is. Okay? So let's go to the dual frame. And the notation is dx1 through dxn. Okay? It's a dual frame. This stuff's linear. This means that dxi applied to ddxj is delta ij. It means that any omega, which is a one form on this coordinate chart, is a linear combination ai dxi, where the ai are functions. You've seen dx all your life, right? When did you learn it in Nepal? It's very high up on the top. Hey, there's dx, man. That's great. Yeah, your teacher says dx. You write some integral, I'll try to write it for you. Integral from something to something f dx. Then somebody says dx is small. So in engineering science they write as delta x, right? And all of that is, of course, just a way of talking about it. It's not what it is. What it is the dual frame. Now that's one definition of dx. However, this is where you're going to really have some fun. Because what's d of x? This is dx. But the question is, what is d of x? So if you have x here, x is a function, right? So you take x and you're having great fun, and you tell your mother, then I took d of x. Now Leibniz was not stupid. That was Leibniz who had the d business, right? He was not stupid. So the claim we're going to make here, I hope you understand the claim, dxi is d of xi. So the notation is good. So not only do you know what dx is, you know what it is in two ways. It's d of the linear function xi, yeah, or it's the dual frame to the vector, it's the dual frame element to here. Well, that's completely clear, isn't it? So what is d of xi applied? I have to check to ddxj. Well, I just told you the definition. It's dxi dxj, and that's of course delta ij. Right? So this states that d of xi is equal to dxi. Okay. That made you really happy, didn't it? Okay, that's good. Well, we've learned something from our episode with vector fields. We've learned that you write them in one frame, you get one thing, you write them in another frame, you get another thing. And you want to know what change. You have a question? A remark?
When you can write also integral of f d mu when you have a measure. Is it like the same thing with operators acting on measures?
No. So this has nothing to do with measure theory. I will discuss an integral in 5 minutes, but so you go to some environments and they say dx is the thing you integrate, right? Now, if you we're coming close to it, he's talking about measures, and this is important also in every subject in applied science. If you have a density, then we're talking about something you might be able to write as a density dx, but measures gets this is a totally abstract thing. So let's check what happens here. We have a coordinate chart u alpha with coordinates x alpha, and a coordinate chart u beta with coordinates x beta. we need to introduce manifolds, that's what coordinates are about, well, and vice versa. We need to know how these one forms change depending on which coordinate you use. Let me try to derive the change. So change of coordinates. So change of coordinates. So we take a look at this thing on U alpha coordinate chart. So this I'm going to write, say, is sum A alpha I D alpha I. I hate writing indices. But sometimes all you see is indices. This conceptual way of looking things simplifies life immensely because you understand what you're doing. If you look at old mathematics, for example, of the early part of the 20th century, even middle 20th century, huge amount of calculations just in indices, and people don't know what they're doing. People don't know what they're doing. They're just doing calculations. This becomes an art form of just pushing around indices. I hate it. I'd like to know what I'm doing. But nevertheless, we've got to know how to change. If we do some calculation, we have to maybe in one index, in one coordinates thing, we want to know what it is in the other.
But can we like take out D? We take out D.
What am I taking out D? I'm not taking any D out. Where?
No, I mean, since D is linear, D is a linear operator.
Linear with respect to what?
To functions.
No.
D is not linear?
Well, what do you think? Let's check it. Let's check what he's saying. D. Oh yes, I see what you're saying. This is what you're saying? Yeah? Yeah? This is what you're saying, Leon.
No.
Huh?
No.
Yeah. And okay, that's true, sir. Now what you're what do you
I
say?
was just thinking of, since it's AI alpha is our functions,
Yeah.
we can put them inside and then write AI alpha, xi alpha in terms of AI beta, xi beta, and then just by the change matrix change.
No, there's something here. I'm sorry. I wrote some. Let's be very careful. You almost convinced me. I get very nervous when you ask these good questions. Let's look here. Let's be a little bit careful, okay? I think what you wanted to say, which is something I should have said, I didn't write it right. You say D of, now, what do you mean linear? D of F times G. Huh?
Y times, not plus B.
So that, and you say, here, the coefficient here is F and the thing where is G. So as you see, this is this.
Okay, it's not linear.
Well, no, it's good that you asked this question. This is exactly what it should be, right? Okay, so it's highly nonlinear. I think what you were originally asking are hoping that I would put this function inside this D here. And of course, we can't do it because it's linear in some other sense, but not in this sense. Okay? Very good question, thank you. So I don't know what to do here, I've got to do this, right? Okay? Okay? And now what I would like to do is see how these coefficients are changing. So what I need to know is that I need to know how they change. And so what that says is that in the simplified notation, AI alpha equals AJ beta. What am I going to do? I'm going to put this AJ beta, so I'm going to write this way, GIJ alpha beta of AJ beta, right? Right? That's just formal. I haven't told you what I think GIJ is. So we now need to compute this thing, GIJ alpha beta dx I, what do I want to do? I want to compute, what do I want to do? Let's erase it. How do I compute GIJ? I put
You
in,
apply it to xi alpha.
I'm sorry, who's speaking? Yeah?
You apply that thing to xi alpha.
Yeah, so I want to apply the right-hand side to, I'm going to apply the right-hand side to dxi alpha. And so I get Gi alpha beta is the same as applying the left-hand side to that as dxj beta applied to dxi alpha, which is dxj beta dxi alpha.
So it's the same as the chain reaction?
This is some form of a chain rule. Yeah. In some languages it's called the Jacobian of the transformation.
No, but it's the same as the change of the basis in the vector field.
It's dual to. So I again appreciate your remark and question. Let me just reformulate what you said. Recall I did the same exact calculation for a vector field. And I got some matrix. This matrix will be a dual to that matrix because of the duality that's going on. Okay. One is called the Jacobian, the other is called...
Doesn't it have the same element? Oh Lord. Doesn't it have the same element? So that means...
Transpose or...
There will be an inverse transpose here someplace. Yeah, and I don't know which is called the Jacobian, I'm sorry. I think the one I did I think this is the Jacobian. This looks like the Jacobian to me. And the other one is the dual matrix. It has to be dual because we're dealing with dual objects. Okay, so we got that right and I'm very happy. Now maybe I'm coming to one of the main points of the discussion. That you can write down and try to sing in the morning to remember it. One forms, pull back, but they are dual to vector fields. Vector fields do not in general push forward. let me discuss this in some detail now. These are just words. Let me discuss the second part of this. Vector fields do not push forward. Let me give you an example. Of what goes on. So, an example of vector fields don't push forward. Let's take a curve, gamma, from the real line in some manifold. But let's say the manifold is at first two-dimensional, as my picture always is. The image of the gamma can look, we discussed this example, the image of gamma could look like this, right? That's very easy to organize. So there are 2 points I want to emphasize. When you're down here at the beginning of gamma, you have this field here which is ddt at this point. This field pushes forward here along this curve. This is the velocity field is the push forward gamma star of ddt. This is the velocity field. You can check it. That's what the push forward is. Remember, we had a lecture on push forward of tangent vectors. This is the push forward of this field. So it's very good. It's very good here, and then it continues to be very good. Push forward is very good. It's very good. It's very good. It's very good. It's very good. Oh, terrible! Right? So I push forward two different tangent vectors to the same point. So I get, in some sense, a multi-tangent vector at that point. I get it doubled somehow or another, right? But that's not a tangent vector anymore, okay? So I try to push forward that thing along that curve. Now, there's another point here. Anyway, at best, we obtain a field, at best, along the curve. If you have a beautiful mapping, say, let me try a different mapping, here's another one, and the curve is a wonderful curve integrating a vector field, for example, then there's no problem. You get a push-forward field, but it's only a field along the curve. I was supposed to tell you what the field is out here. You don't know. It's only along the curve, along the image. Okay, so the 2 points here. The multi defined in this is one big point, and the fact you're not getting a field anyway. You're not getting a field on the whole manifold anyway. So that's an example to vector fields do not push forward. One form is pull back. So I have to tell you about the pullback of a one form. This is beautiful. You have a mapping from a manifold to another manifold. This is even interesting when it's in Rn or something. Let's say this manifold is dimension m, this manifold is dimension n. Okay? And as a result, there's going to be a mapping, pullback mapping, from one forms on the image space to one forms on the original state. Okay? Now let's try. Okay, here we go. So, I have to take a form on the image space and pull it back.
No, it's and nothing.
Hmm?
It's and nothing.
Thank you. N. So take a form on the image space and I want to pull it back. So, I want to pull it back. And when I pull it back, I want to apply it to a vector field. At a point, let's say, I don't care, at a point P. Well, that's not so hard. I take omega at f of p, you can localize, I told you that's no problem, and apply it to the push forward of the field at p. Again, let's go through this slowly. So many letters, it's terrible. So I take a form. I want to pull it back. In mathematics, if we have the star upstairs, it means pull back. If you have the star downstairs, it means push forward. Okay. So I want to pull it back, so I want to get a form on, oh, I didn't say that. So X should be a vector field on M. So I want to apply this pullback to X. And I want to tell you what it is at a point P. What I do is, I look at omega at f of p, and evaluate it at the push forward at p. Let's look at my bad example. So at my bad example,
So, shouldn't you write omega and f of p at the end? Because you wrote p in the end in the first part, and then you wrote it.
you mean here?
Yeah.
I'm applying
Yeah.
a function to an argument. Oh, yeah, no, I'm doing exactly what I want. I'm applying a function.
No, I mean in the first row you have in the second last row there. You have an operator, not an operator, one form applies to a vector field evaluated at a point.
Yeah.
And in the second row you have a vector, one form evaluated at one point in a vector field. I mean it's you switch the.
No, that's the point, I do. There's some, therefore it's confusing, so we should discuss it. Okay, let's go through. This should be a one form, and that means when you apply it to a vector field, you should get a function.
Yes.
I'm telling you what that function value is at this point. So this side is a number. Okay. This is a one form. This is one form at a point. So it's dual to the tangent space at that point.
No, I understand what you mean, but
Well, that's a tangent vector.
no, why don't you put f of p at the end? That's my question. Because, so that is the same as the first row.
Here.
No, f of p, the one in the middle. Yeah, why don't you put it in the end so that it's like the first row? I mean.
No, because this is the one form evaluated at f of p. This is another very good point. I confused him and he asked a good question. So other people should learn from that. So I confused him and he asked a good question. Remember I said locally you can take something on a big set and restrict it. You can even evaluate it at a point. So at a point, so this thing, let's suppose this thing nearby is equal to some AI dx, or maybe it's over here, it's dy, dyi, okay? So at a point, at this point, that's what I'm talking about, f of p is some, these are functions evaluated at f of p, and these things evaluated at f of p. These things evaluated at f of p means the dual basis to the vector fields at f of p. So I mean exactly what I wrote, it's just that I hadn't explained enough of this localization process. You okay now? It's this local global nano, right? I can restrict as much as I want, and here I restrict it right to a point. Okay, so I just evaluated the point. So again, I can pull back forms and I cannot push forward vector fields. You see what happens here, I started to say, and then correctly so, you interrupted. If I have a form over here, Omega, say here, well, I do all this thing, and here, you know, I push forward and I evaluate, I push forward, evaluate, push forward, evaluate. I get to here, I push forward and evaluate. Right? Then I come back around here and I push forward and I evaluate again. That's okay. I'm evaluating again. I just happen to be evaluating again. In fact, in a different direction. You see this? In this case, when it's really transversal like this, I'm evaluating one time in this vector direction. It comes back around, I'm evaluating this time in this vector direction. So I might even separate these 2 points with this one form. Yeah? Okay? So that's what happens. You cannot push forward tangent vector because they cross and you get multi-valuedness, but you can pull back forms. Okay.
Professor, what is f of star while the star is at the bottom of that?
So
Yeah,
this is a definition,
yeah.
and this star was talked about in the lecture by Anna. And just to remind you, okay, f lower star. You see, this looks, another good question, thank you. This is darn mathematical notation. If lower star is push forward, it looks like a push forward. It is a push forward, but it's a push forward from the tangent space at P to the tangent space. From tangent spaces to tangent spaces. And it's defined f star of a tangent vector applied to a function, and I'll emphasize the tangent vector is defined at P, is the tangent vector applied to the pullback of the function. But only at the point. And if you think slowly about it, it's only what I'm talking about here. You have major problems trying to define this thing locally. You cannot do it. Again, one forms pull back, differential forms in general pull back, and vector fields do not. There's a major difference between forms and fields. And I like forms in terms of the structure. So one last thing. You can have fun doing a little calculation here, I think. I'll leave the calculation to you. Suppose you have a curve. So let's follow the notation here. Let's let n be the real numbers, and let's let n be. Well, let's let this be an interval. in the real numbers, and n be R2. So here's R2, and here's some crazy curve. This is going to be a curve, gamma, from n to n. Okay. And now, on the real numbers, I'm going to take form omega f dx plus g dy. I told you, it's the basis of the spectral module. So dx and dy are the basis, coefficients are functions. Really only needs to be defined near the curve, because we're going to talk about the integral. I want to integrate over gamma omega. Okay. Now we're coming to engineering science, where we have delta and all this crazy stuff. Well, this is integral. Well, let's call this integral to make life easy. 0 to 1, gamma, pull back, omega. It's the only possible definition of an integral, at least for smooth functions. Okay. Now you can have some fun. And I will write a picture here that you should show your physics professors and to make them mad. But in Jacobs University, physics professors, very nice people, they understand everything, it's great. So here I'm going to write in blue omega. Well, omega is f dx plus g dy. I'm telling you, in applied sciences, many people think of forms as vectors. Okay? It's actually a covector. If you think of tangent vectors as being vectors. Now, you want to compute this integral. So you want to compute the pullback of this form. Okay? Guess what? Here, you have gamma point. This is the push forward, gamma point at the time t. This is the push forward. This is the velocity vector x point y. If you think for half a minute what this calculation means, you get the answer f, let me go very slowly, f of x of t, y of t, function of two variables, x dot of t. This is how you're going to compute this pullback of this form along this curve where I have this velocity vector, g of x of t, y of t, y point of t. So this integral becomes the integral from 0 to 1. Let me write this down. F, I'll write it down slowly again. F of x of t, y of t, x point of t, g of x of t, y of t, y point of t, dt. That's it. Now, that term in the middle, you learned about in school. If you think of that one form as a vector, at that point, this is the vector. If you don't mind, I'm going to write it as a vector, fg. Okay? This is terrible, but okay. What have I written in the middle of that integral? Can you read it all right? F x point
It's a
g
scalar
y
product.
point. What?
It's a scalar product.
Scalar product. Okay? Right? It's a scalar product. Well, scalar product, omega, gamma point. Right? Some people call this work. Now, that's an important concept, everything. But scalar product is something in geometry, right? If you're in a field here where the scalar product is not constant, for example, it's not the standard scalar product. I mean, this is not scalar product. Suppose the scalar product is moving wildly some way. Right? This is really not that. It's a formal expression. This scalar product really means you apply, it really means this. Okay? It means you pull back the one form to the interval and you integrate it. It is not a scalar product. What?
Why did we learn in other classes that the work is the integral over gamma of the vector field, not of the... Because somebody decided to call that a vector field. So I think I'm very happy that you say you did learn that, right? So work is defined to be the integral of the, if you're in a force field somehow or another, you have a curve, right? Work is defined to be the integral of the scalar product. Which makes sense, right? Because you think of it as somehow projecting the pulls in that direction.
you're considering the force in that direction. I mean, it's a very reasonable thing, right? I emphasize scalar products are additional structures. Scalar products don't exist in this picture.
So the first is the one form, is not a vector?
The one form is a one form. You are precisely evaluating, you have the tangent field along the curve, and you are evaluating the one form along that tangent field. Basta. There is no scalar product here. It is only a notation in the Euclidean plane. Right? If you somehow or another think the correct geometry here that dualizes one forms and vector fields is the Riemannian geometry of the Euclidean plane, then I'll buy it. Do you understand what I'm saying? You have a vector and a covector, and you would like to say this covector is really a vector, and so you make projections and all of that stuff. You have to convince me that this scalar product is the right scalar product to use. Yeah? That means the flat Euclidean geometry is the right scalar product, then you can call it a vector. If you want. But it's not a vector. It's a one form. And one forms can be integrated, and vector fields cannot be integrated. The reason one forms can be integrated is you can pull them back. One form can be integrated because of being pulled back. Vector fields cannot be pulled back. You can't integrate vector fields. I'm sorry. Unless maybe you're lucky that you have some duality that gives you a way of interpreting a vector field as a one form. Okay? This is an isomorphism between the space and its dual space. This is not canonical and is given by nature in certain situations. Okay? That's a really fundamental point. And therefore, I like one forms a lot better than vector fields. Okay? So, thank you very much. See you next time.